Thank you. So thank you everyone for waking up very early for the course. So my first talk today will be about the basics of pattern recognition for neuroimaging. It's going to be a very introductory talk, and you will get more advanced through the day. And let me just see if it works. Okay. That's the outline of the talk. I start with a brief introduction about the pattern recognition framework. Then I will discuss the main differences between mass univariate and pattern recognition analysis. I will, after that, introduce the concept of linear predictive models for classification and regression. And after that, I will talk about two concepts that I think are important to the field, which are regularization and kernel methods. And if I have time, I will briefly show a demo, but I'm not sure if we'll have enough time because of the question, but let's go. So pattern recognition. So for people who might not be familiar, pattern recognition is a branch of machine learning that has the aim of finding some patterns or regularity in the data that can be used to take actions, such as making predictions. And there are many examples of applications from handwritten digit recognition, face recognition, recommendation engines. Nowadays is used for finances. And actually, if you have a smartphone, it's very likely that you have a couple of pattern recognition algorithm on there. And of course, it's used for neuroimage data analysis, and that's why we are here today. And the idea is that we try to learn something from data to make predictions. And just a very brief introduction is that there are different types of learning. Today I will be talking mostly about supervised learning, which means that when we train these algorithms, we have the input and output, so we have labeled data, and examples of this type of application, classification and regressions. But there are other types of learning, such as unsupervised learning, where we don't have, the outputs, we just have the input, so we train the algorithms with unlabeled data. An example is clustering analysis, and you'll be hearing more about that later in the day. And there are other types of learning as well, such as reinforcement learning that involves actions and rewards, and these we can find examples in robotics. But I will be focusing on supervised learning in this talk today. So basically, in the supervised learning framework, the idea is that we are interested in learning a relationship between input and output. Maybe it doesn't really help with the... So we go here, and we don't have an explicit mathematical model available. And here, just in this example, what I have as input, we have handwritten digits, and the outputs are the labels, the real labels from these digits. And we want to learn, a function that does this mapping from input to output. If we don't have, this explicit mathematical model available to go from input to output, we can use the machine learning approach, which means we learn these functions from a series of examples. And we have two phases, the training phase, where we give examples of this relationship we want to learn. So we have the patterns here and the labels. And the outcome of the training is a function that does this mapping, giving the input, gives the output. And the second phase is the testing phase. So given a new pattern, we can make predictions using the function that we've just learned during the training. So that's the basic framework. So how does it can be applied to neuroimaging? So we can use this framework to train classification models. And here, the patterns will be brain scans or any feature derived from brain scans. And then here we have a classification model because we are interested in giving and training a classifier to distinguish between different classes, can be different groups as patients and healthy controls, or can be different cognitive tasks. And we have these two phases. So during the training, we learn this predictive function, which we can visualize. I will be talking a little bit more in the next slides about it. And then you can apply it to make prediction. For a new brain scan, you can make a prediction. The same type of approach can be used for regression models. And so it's the same framework. The only difference here is that we are interested in learning the relationship between the brain and a continuous measure. Can be a clinical score, can be age. And then once we train the model, we can use these models to make predictions. So given a new brain scan, we can predict the score, and could be predicting the age from the brain scans, for example. So how what are the advantages of using pattern recognition? So why it became very popular for analyzing neuroimage data. I think the first applications started over the last 15 years and has been increasing and increasing the number of applications in the field. I will emphasize two advantages that I think are quite important. One is the fact that it's multivariate, and because of that, it can be more sensitive to detect subtle and distributed effects in the imaging. And there is a second advantage I think is also very important that sometimes people forget to talk about then, is that pattern recognition as part of machine learning has a predictive framework, which means that it provides predictions for new examples. So we don't only fit the model, but our model is able to make predictions. And this enables a whole range of new applications, such as clinical applications where people are interested in making decisions about a single subject, for example, for diagnosis and prognosis, but also enable neuroscience applications such as mind-reading approach. So from the brain, we can make predictions about what the subject was thinking or doing during an fMRI acquisition, for example. Now, since I'm talking about the advantages, I would also like to emphasize some of the differences. If you've been using, neuroimage data in your lab, you probably already used mass univariate analysis, and I think it's important to understand some of the differences, in using one or the other type of framework. So with standard statistical analysis, often called also mass univariate analysis, what we often do here is an example. I have an fMRI data. So what we often do is that we look at each voxel in the imaging, and then we look at the time series of this voxel. And normally we are interested in seeing which voxels in the brain are responding to a specific experimental task. So what we do, we fit a model to the voxel time series, we estimate some parameters, we apply some statistical tests, and then we repeat this process to all voxels in the image. And after that, we need to do some corrections for multiple comparisons because you have 100,000 of voxels and 100,000 of tests. And the output of this type of analysis will be a map, showing which voxels passed this statistical test. So we have a statistical parametric map that shows where in the brain you have a significant effect of interest. So that's the standard mass univariate approach. With pattern recognition analysis, we look at the data from a very different perspective. Here we have this, I already explained, you have the training and the testing phase, and here we give the whole pattern, the whole brain, for example, or can be the pattern within a region of interest, but we give the whole pattern to the algorithm. So we don't look at a single voxel at a time, we look at the whole pattern, and the outcome is this predictive function, and then we can make predictions from it. And again, here we also have as output, let's see if I can emphasize here. In both cases here, we have maps, but one point I want to make is that once we have our predictive function, we can visualize a map that you'll be hearing a lot about it today, but I just briefly mentioned that, this predictive, we can think of it as a predictive pattern, but it has a very different meaning from the mass univariate analysis, because with the statistical parametric map, we did a test at each voxel, and we can make inference at this single voxel level. But with pattern recognition, we are using the whole pattern. It's a multivariate approach, so it can be sensitive, but also it has the issue that we cannot make inference at the voxel level. We can only make inference at the pattern level. So I think that is something important to have in mind. Now, if we go into neuroimage data, how we use neuroimage data in pattern recognition. So the first thing we have to do, not only for neuroimage, but for any type of data that we want to use for pattern recognition, we need to extract features from the data. And basically, if we think of neuroimage data, brain scan is a three-dimensional matrix of voxel, and what we have, the first thing we have to do is to extract some features from this matrix. And the simplest thing we could do is to consider each voxel in the image as a feature, and then we can construct, build a feature voxel, a feature vector that has the dimensionality as being the number of voxels in the image. That's the simplest thing you can do. Of course, you might want to use just voxels within a region of interest if you have a specific prior, but the idea is the same. You just have a smaller feature vector here. And there are also, of course, you can extract features in a more complex way. For example, you can average the voxels within the regions to have volumes of interest being your features, or you can have connectivity measure or thickness, cortical thickness. So there are different ways that you can extract features from your image data. And actually, there is a lot of evidence now that the way we extract features from the neuroimage data might have a higher impact on your performance than the machine learning or the pattern recognition algorithm. So it's something you should think of, how to extract features from the data. Now I want to move on to give a bit of intuition. Once we extract these features, how we train the models. Today I will not have time to go into the deep technical details, but I want to give first some intuition about how these methods work, and then a little bit of the maths, but first I think it's important to get an intuition. So the way we can get an intuition is starting with a very simple toy example. So we extract these features, and I will just have a toy example where we extract two features from the brain, and then we have this two-dimensional feature vector, which is easier to visualize and understand things in 2 dimensions. So what we do then is that we can plot each of these brain scans, or if it is images, as a point in this feature space. Now we have this image, you have, value of feature 1 by value of feature 2. So our brain scan, our feature vector is 1 point in this space. And we can do the same for all training examples that we have. And actually, when we train a classifier, what we are trying to do is we are trying to find a boundary in this feature space that separates these 2 groups. And of course, here it's just a toy example. We have these 2 dimensions, and then the separation here is a line. If we had 3 dimensions, the separation would be a plane. And in higher dimensions, which is what we normally have with neuroimage data, we have a hyperplane. But the concept, the reasoning is the same. We just want to find a boundary in this space that separates the 2 groups. And there are different algorithms that will correspond to different boundaries, and each of them will have different properties, but basically they all separate. The goal is to find a boundary that separates the data in this space. And once we found this boundary, what we can do is, given a new image, we can plot it, and we can make prediction. And the way we do it is that once we found the boundary, we have a weight which is normal to this boundary, and we project the data onto these weights. And then if this projection is below or above a certain threshold, which is defined by the boundary, we classify it as belonging to one or the other class. And basically, what we do with classification, we want just to cut this feature space into 2 parts, and then to classify images in one or the other group. So the same type of idea can be applied to regression models, but in regression the situation is slightly different, just because we are not interested in finding class. We are interested in predicting a continuous variable, but the idea is the same. We extract some features from the images, and we can plot our training images as points in this feature space. But now you want to find a model that predicts the data in a linear way, in a continuous way. And so basically, and then once we find the model, we can make predictions for new examples. And differently from the classification here, we're not trying really to cut this space into 2 parts. We're trying to find a model that makes continuous predictions. But the idea is very similar. We are trying to extract these features, and then we do the training in this feature space. And in both cases, what I showed you, I was talking actually about linear predictive models, and linear predictive models, both classifications and regression models, are parameterized by a weight vector and a bias term. And actually, these are the parameters that we learn from the training data. And once we learn these parameters, the general equation for making predictions for a test example that I'm representing here as X star is this equation. Basically, the idea is that see if I manage to use the the pointer. So the basic idea is that once we have a test image, we compute the dot product between the test image and the weights plus a bias, and then we have a value that will correspond to our score in a regression, or if we are working with a classification, will be the distance to the boundary. And just to emphasize, these, the W and the B are the parameters that we learn or we estimated from the training. So that's what we do during the training phase, is to learn this predictive function. So in the linear case, W can be expressed as a linear combination of the training example. So W is given by this linear combination here, where xi are representing our training example. So basically what we really learn is the alphas, which is the contribution of each training example for the predictive function. So, and the reason why I'm talking about this W is because it has the same dimensionality of the original data, and we can visualize it. Basically, we can visualize it, and I will not go into details because you have a talk later where Jessica will be going deeper in about what you can say and you cannot say about these weights, but basically, just want to briefly mention is that, this W can be visualized. It shows the relative contribution of each feature that we used for the decision or predictive function. And it's important always to remember that we cannot make local inference on it because it's a multivariate approach, but you'll be hearing more about that later today. So moving on for the challenges in neuroimaging. When we apply this type of approach to neuroimage, we have an important challenge, which is the fact that in neuroimage applications, normally the number of features will be higher than the number of examples. And that is, it means that we have a conditioned problem. And if you might know from statistics that if you are trying to estimate parameters and you have more parameters to estimate than data points, you cannot do that because there is no unique solution for this problem. But actually we do, we make predictions from whole brain. You have 100,000 of parameters that we estimate, and we have hundreds of examples, and it still works. So actually there are ways that you can overcome this problem, and I will just talk about some of them and emphasize one of them that I think is the best one, in my opinion, but there are different ways we can approach this problem. One is you can decrease your number of features to solve the problem. And you can do that by just using regions of interest or averaging your image to have summarized the features into regions instead of voxels. You can use some feature selection strategy to decrease your number of features. And you can also use approach such as searchlight, where you look at the local neighborhood, multivariate. You have a sphere, and you just look at the multivariate information within this sphere, and then you travel with this sphere through the brain. But the approach I will be talking today, which I think is a more general approach, is to use regularization and kernel methods. So I will talk about these two concepts now. Regularization is actually is not only in machine learning, but is a technique that we use to try to solve ill-conditioned problems or ill-posed problems and prevent overfitting in statistics and machine learning. The basic idea is that we are trying to find this W, the predictive function, but there is no unique solution. So what we do is that we add some additional constraints to our problem to make it unique. So basically, regularized models, we find this W, minimize an objective function that consists of a data fit term, E, and a regularization term. So just to show here, and then see if I can. So we have, that's the optimization problem. If we just have the data fit term, which is a loss function, we will not be able to solve this problem because it's a wheel-conditioned problem. But because we add an additional constraint, this regularization term, we make the problem unique, the solution unique. We can make it unique. And we have this parameter here that I'm calling lambda, that is a regularization parameter that controls the trade-off between these two parts here. And it's a parameter that needs to be optimized using nested cross-validation, which I believe you'll be hearing in the next talk more about it, but I won't go into the details here. But what I want to say is that most of the many machine learning algorithms that we used are particular choices of loss functions and regularization terms. And to give some intuition, regularization, it should correspond to some prior. You have to constrain the problem. And hopefully we can use a regularization that makes sense to our data. I will just show an example in the next slide how it can affect the W, the choice of regularization. And I believe you will also be hearing more about that later through the day. But the idea here is that we need this regularization in order to work with this very, very high dimensional data when we have small sample sizes. So I just want to show here an example to give. I won't have time to go deep into regularization, but what I want to show to you to give some intuition is that when we look at these weight maps, it's not only, they are not only affected by the data we have, but they are strongly affected by the choice of regularization, which we have to make anyways. We have to make a choice. And what we are seeing here is that, we have weight maps for classifying fMRI during a visualization of pleasant versus unpleasant pictures. And all models here use the same loss function, which is a squared loss, and the only difference between them is that the regularization that they use. So there is lasso, elastic net, total variation, Laplacian, sparse total variation, and sparse Laplacian. And what you can see is that depending on the regularization used, the weight will become more sparse or less sparse, or more smoother or less smoother. So this is, I just want to highlight, this awareness that actually the regularization use affects a lot the map you get. And you can see that the accuracy for the models doesn't really change much, but the way the maps look like change a lot. So it's just something to be aware. When you see this in a paper, the map you're seeing is not only about the data, but it's a lot about the regularization, that if you work in high dimensional sets, you have to make a choice. So hopefully you make a choice that makes sense according to your assumptions about the data. So the other concept I want to briefly touch is kernel methods. And the idea here is the use of the kernel methods are the advantages to make things computationally more efficient. I'll try to give the intuition right, but basically kernel methods is also a branch of machine learning, is a framework that is quite powerful for investigating relationship in the data in general, such as classifications and regression. And it consists of two parts: use of a kernel function and a learning algorithm that works with the kernel. And the main advantage in case of neuroimaging is the computationally efficiency, but also you can use the kernel trick for nonlinear kernels, which I would say, I probably will talk about that in the next slide, but most of the applications in neuroimage data have been with linear kernels, and I will, in the next slide, talk a little bit more why this is the case. So kernel function. Kernel, is a function that, given two patterns, returns a number characterizing their similarity. And the simplest way that we can measure similarity between two vectors is the dot product, which corresponds to the linear kernel. And the idea of using the linear kernel is that we have a data matrix if we work with neuroimage data. And imagine that we want to do whole brain. So we have 100,000 of features or 100,000 of voxels, and we have 100 subjects. So the data matrix is huge. And it's not very easy or efficient to load these in the computer to train the algorithms. So what we can do then, we can use a kernel function to compute this kernel matrix. It means that we compute the pairwise distance, the pairwise similarity across all our examples, and then we have this matrix that really summarizes our data. Here we have each entry in this matrix corresponds to a dot product between two of the images that we have. And so we can work with this kernel matrix instead of working with the data matrix, and make things much more efficient, in these high-dimensional settings. It's quite advantageous to work with them. And here I'm talking about the dot product is a linear kernel, but basically there are other types of more, general types of similarity measures that are nonlinear, such as Gaussian kernel and polynomial kernel. And what these nonlinear kernels do is that they actually, one way of thinking about them is that they map the data into a higher dimensional space. So far, there are little evidence that they are advantages for neuroimage data, because neuroimage data is already in a very high dimension. So if you have a problem with lower dimensional, it might be advantage to use them, but in higher dimensional data as neuroimaging, there is very little, as I said. And in addition, you cannot easily visualize the weights, so they become, the approach become much more like a black box if you start using nonlinear kernels. But as I said, one reason why they might not be advantage is the smaller sample size we have. Maybe when we start having millions of brain scans, then using these nonlinear kernels might become more advantageous and enable us to explore nonlinear relationship in the data. So now I just move to show briefly how we can make predictions with the kernel methods and why they can be more computationally efficient. So if we start with this definition that I gave before of the predictive function, here we are calling primal representations because, you know, the parameters that we want to learn here, basically mainly the W and the bias, but the W, it has the dimensionality of the brain or of the features, which is 100,000. So we can replace the definition of W by the linear combination of training examples. So we sort of reparameterize the decision function here, or predictive function, and what you see here, that's the definition I gave of the kernel matrix. So we can arrive in another definition of the predictive function. Now we are expressing it in terms of the kernel, and the advantage here is that instead of having to estimate, you know, 100,000 of parameters, we can estimate hundreds of parameters because the alphas corresponds to the number of examples. So actually, you can go from one to another representation. They are equivalent, but if you have higher features, you know, number of features than examples, it's more efficient to work with the dual representation and kernel approaches. And many methods we use are kernel methods, such as support vector machine, kernel ridge regression, Gaussian process, relevance vector regression. These are all examples of kernel methods that we use. Just touch very briefly because I'm running out of time. Another advantage of kernel methods is that we can use it to combine different types of data easily. You know, it's a very nice framework that we can use to combine, for example, multimodal information for prediction, and multiple kernel learning is an approach that can do that. And in MKL, you know, your kernel is a linear combination of basis kernel, and what we learn is that you can represent each neuroimage modality, for example, by a different kernel, and you learn a contribution of each modality for the prediction. So the advantage of using this approach is that you learn, you know, the decision function, and you learn the contribution of different kernels that can correspond to different modalities, or, for example, different brain regions to your prediction. So it's quite a nice way of combining different types of data for prediction. Yeah, I just want to finish showing this overall, just a summary of the pattern recognition framework. You know, you start extracting some features from the data. You start with the image and the labels. You extract some features and labels. So then we have to split the data between train and test. With the training data, we train the model. The outcome is this predictive function, which is applied to the test data. And here you measure some performance that can be accuracy in case of classification and mean squared error in case of regression. The point I want to make, just finishing the talk, is that always you have to estimate the performance of your model using the test data, never the training data. So just a take-home message, and I will just finishing pointing to, I will not have time for the demo now, maybe after the questions, depending on how long they take. So that just want to point to Pronto, which is a software that implemented in the current version, kernel methods for pattern recognition. We actually have a talk tomorrow in the open science room, and we have a poster the following day and another demo on Wednesday. I think Jessica she will show the number of the posters and the times of the of the demos. Just want to finish acknowledging everyone that contributed to this talk and the Pronto team. And there are some useful reference if you are interested. And now I think we can move on to the questions.
Yes.
Oh, thank you.